Okay, good morning, ladies and gentlemen. This is Professor David J. De Los Reyes. The date for this morning will be January 4, 2025, and the time is around 2:09 a.m. Okay, my topic for this morning will be a continuation of my long video format topic, DC circuit, and we are now, or I am now on lesson number 24. Lesson number 24 actually is a continuation of the so-called Nodal's theorem. Okay, let's proceed. The subject matter for this morning will be a long video format topic under my long video format topic, DC circuit. This is lesson number 24, and the title of the topic is actually Nodal's theorem, example number 2. I already have discussed the concept of Nodal's theorem, and the last time around, I discussed or I give you an example problem number 1 under Nodal's theorem. Okay, it's a complicated problem because the circuit involves 3 voltage sources, and one load is connected in parallel with them. And the problem is asking for the current through that common load with the 3 given voltage sources. If we try to use the other method of solution, the solution is actually very long. But under Nodal's theorem, we derive already the formula on how to compute for the current for that part of the circuit, the load RL. Okay, so it's just a matter of the so-called using that derived formula. Okay, then substitute the given values, then simplify, and we could now compute for the current IL by using Nodal's theorem. Because the simplest solution for the last problem, the last time around, is actually Nodal's solution. So for this morning, I will be giving you the last example under Nodal's theorem concept, because the next time around, I will be discussing the so-called another method of solution of circuitry, that will be the star, or the so-called Y and delta configuration. That's another variation of circuit variation. Okay, it's another type of circuit under the study of this circuit. Okay, let's proceed. The given problem, I just give you the figure. For tonight, the problem is just simpler than the last time around, because I just give you tonight, this morning, 2 voltage sources. I got an 18 volts here and a 16 volts. Their internal resistances are actually 6 ohm for 18, 4 ohm for the 16 volt. And the common load to these 2 voltage sources with the given internal resistances, the load RL is actually 24 ohms. Okay? And the problem is asking what will be the current passing through this 24 ohm load here. So this IL here refers to I sub 24. Okay. The problem is asking what will be the current with the subscript 24, meaning the current passing through this 24 ohm load with these 2 given voltage sources, and with the respective internal resistances 6 ohm and 4 ohm, and their value is actually 18 volts and 16 volts. Okay, I will try to check my camera. It looks good. Okay, let's try to bring out the solution by using Nodal's theorem. This is a simple problem now because like what I said, I have derived the concept on how to bring out the current passing through this load RL here. But before we could compute for the current passing here, we must have to compute for the voltage across these 2 nodes here, or 2 junctions. This is referred to as V sub L, the so-called node voltage. Okay, the voltage across this, if we try to measure this using our multitester, it will be the so-called node voltage or junction voltage. So before we could compute for the current passing here, we must have to compute first the voltage across this. And according to Nodal's theorem, the formula and how to compute for the voltage across this is actually given by this formula here. Okay? It is given by this formula. And all the values within the equation are all given. So it's just a matter of substitution now. Okay, but we must have to be accurate on the computation of the numerator and the denominator because it involves fraction. Okay, so upon the computation of this of L, we could go back to the equation IL equal to BL over RL. So if BL now is computed, we are now given RL, so we could now compute for IL. But before we could compute for IL, the current passing through the 24 ohm load, we must have to compute first for B sub L. Okay? Let's try to bring out the equation for B sub L. For two voltage sources, okay, the numerator will just be simply voltage source number 1 over R1, voltage source number 2 over R2. Okay, it stops there because there are only two voltage sources. And the resulting denominator will be the summation of 1 over R1 plus 1 over R2. There are only two voltage sources, so it stops at R1, then R2, and the last part will be RL. We add up RL, right? So this is with the subscript 2, subscript 2, subscript 1, subscript 1, and the last part here is RL. Okay, let's try to compute the value of the numerator and denominator separately, so we will be systematic in our computation. It is a simple solution now because we are now given the equation and how to compute for B sub L. Let's try to compute for the numerator. The numerator is the sum of E1 over R1 plus E2 over R2, so we will compute their values separately. E1 over R1 will be 18 over 6. E1 is 18 volts, R1 is 6 ohms, so this will become 18 over 6 and that will be 3. E2 over R2, E2 is actually 16 volts, R2 is the internal resistance of voltage source number 2, it's 4 ohms, so this will become 16 over 4, and 16 over 4, luckily it's 4. Okay? So we are now given the value of E1 over R1 and E2 over R2 because we solve it separately before we will substitute on the complicated equation. It's not complicated, but it seems complicated because it involves fraction. Okay, let's try to compute the value of the denominator separately. It's the summation of three fractions, right? So this will be the quantity 1 over R1, 1 over R2 plus 1 over RL. We are given R1, we are given R2, and we are given RL, so it will become, this will be 1 over 6. R1 is 6 ohms, R2 is 4 ohms, and the value of RL is 24. This is closed quantity. This value here should be less than 0.5 because 1/6 is a very small number, 0.2 something, and 1/4 is 0.25, and 1 over 24 is actually a small value. So if we try to take the summation of this, okay, it will be 0.4583 by using our calculator. That's just an easy one, guys. It's just the so-called reciprocal thing. I'm using my solar calculator for 20 years. So I will just display 6 here. I will take the reciprocal. We are given the value 1 over 6. I will add up 1/4. Plus open quantity. I will display 4. I will take the reciprocal. Close quantity. I add up the sum of 1/6 plus 1/4. The last part will be plus open quantity. I will display 24. I will take the reciprocal because this is 1 over 24. Closed quantity. Then I will press the equal sign. This will now be the summation of the three fractions. It's 0.45833. 0.45833. This is 0.45833. So this summation here will be 0.45833. Okay, I will try to check my camera. Okay, my camera is now aligned. Since we are now given the value of the numerator and denominator separately, we could now go back to this equation here. It's just a matter of substitution now. So BL now will be the sum of the numerators, which is 3 and over 4. This is 3, this is 4. And the single summation of the denominator is 0.45833. That will be 7 over 0.45833. This is almost 1/2, so the resulting BL here should be almost times 2. So this is 15.27 volts. So the voltage across this will become 15.27 volts. The voltage across this, right? And the voltage across this is the same as the voltage across the 24 ohm load, because this portion here is in parallel with this. So whatever voltage that will appear here, it will be equal to the voltage across the 24 ohm load. So by using the first equation here, isobel now, the current passing through the 24 ohm load will be the computed value of isobel 15.27 over 24. And that is 0.636 amperes. So the current passing here is 0.63636 amperes. Okay, we are now given or we already have computed the current passing here by using Nodal's theorem. Okay, let's try to check the validity of our answer. To check the validity of this, we could either use the previous topics, Norton's theorem, superposition theorem, Thevenin's theorem, but I prefer the so-called superposition. For the superposition, it will be an easy one. For the superposition, we'll try to consider first the 18 volts. Okay? So we short the 16 volts, so it seems this 16 volts is gone, right? We short out the 16 volt. Okay? If we short out the 16 volt, if we try to take the total resistance, the direction of the solution here is that we must have to compute for the voltage across this. So we could compute for the current passing through the 24 ohm load due to this 18 volts. So we will be using our knowledge of the so-called series parallel combination. And before we could compute for the voltage across this, we must have to compute first the total current emanating from 18 volts. And to compute for the current delivered by this 18 volts, if this 16 volts is shorted, we will use the series parallel. And if we try to simplify the resistance will be this 4 here and this 24 will be parallel. They are in parallel, right? So if we try to take the single equivalent of this one, it will be the product of 24 times 4 over the sum of 24 plus 4. What will come out will be, it's a small value. Okay? It should be a value less than 3. And to compute for the total resistance now, it will be the single equivalent of this one. I am now just verbally explaining the solution, the simplified checking. Okay? It will be the single equivalent of this plus 3. That will be the total resistance. So if we try to compute for the total current emanating from this 18 volts, it will be 18 divided by 3 plus the single equivalent of this one. Okay, we could compute for the total current. And the total current is actually, no, it's not. Upon the computation of the total current, the voltage across this now will be 18 minus the total current times 6. And what will come out for base of L will be 6.54. So, by using the 18 volt source, okay, the voltage across this is 6.54. Okay, and since this one here is in parallel with this, whatever voltage that will appear here will be same as this one, we could compute now for the current passing through the 24 ohm load due to the 18 volt source. And that current is 0.727. Okay. For the next part of the checking, okay, we'll short out this 18 volt source here. We short it out. Then this 16 volts will remain. Okay. So again, to compute for the total current emanating from the 16 volts when this 18 volt source is shorted, okay, again, we will use the series parallel. And this 6 here and this 24 is in parallel. So it seems there is a 24 over here if we try to transfer it, right? So this is 24. They are in parallel with the 6. So the single equivalent of this one will be the product 24 times 6 all over the sum, which is 24 plus 6, which is 30. Okay? Then we could compute for the current emanating from this 16 volts over here. So upon the computation of the total current emanating from the 16 volts here, the voltage across this portion now will be 16 minus the total current emanating from the 16 volts times 4. And that's B sub L due to the 16 volts here. And what will come out will be 8.727 volts. Right? The voltage across this due to the 16 volts is 8.727. Okay, I just give you the summary of the computation. I verbally explain it, right? So if we try to compute for the current passing through the 24 ohm load, okay, due to the 16 volt source here, when this 18 volt source is shorted, it will be the ratio 8.727 divided by 24, and that will be 0.3636 amperes. Okay, so actually the current passing through the 24 ohm load will be both downward. They are both downward. Due to this 18 volts here, the current passing through the 24 ohm load is downward. Due to the 16 volts here, okay, the direction of the current given by the 16 volts is still downward. So if we now try to consider the two voltage sources, the total current passing through the 24 ohm load will be IL1, the current coming from the 18 volt source, and the current coming from the 16 volt source. And they are actually designated by this one, two values here, 0.2727 and 0.3636. So if we try to take we are just taking the algebraic sum. They are not vectors, it's just a real number for DC circuit. So the total current passing through the 24 ohm load now will be 0.2727 plus 0.3636. And what will come out if we try to take the summation of this, it will become 0.63636, same as this one. Okay? So our solution is correct because upon checking it by using the superposition theorem, the current passing through the 24 ohm load is 0.63636, and by using the superposition theorem, the value is still 0.63636 amperes. Okay, I will try to check my count. Okay, that's it, guys. So this will be the last part of the study of Nodal's theorem, because I already have given you the concept I have given you 2 example problems. So the next time around, I will be discussing the star or the star and delta method of calculating resistances in DC circuit. Okay, good evening, good morning from Los Angeles. This is Professor David J.